Hi, in this video we will learn how to solve systems of linear equations over integers modulo a prime number. Let us recall that when you have a linear system, the coefficients and variables can come from either real numbers or integers modulo a prime number. Remember, integers modulo prime numbers have only finite number of elements, and you can add, you can multiply, everything is modulo p, that prime number. And well, if the coefficient and variables are coming from R, then we say it's SLE over R, or we say it's an SLE over ZP. The solutions of such SLEs come from, well, if we have n variables, then the solutions are vectors with n components. So this will be from Rn, and this will be from Zp to the power n. And since Zp is finite, well, only has p elements, that means that, well, we have p elements for first component, p element for the second, and so on. You get p to the power n. We have only p to the power n vectors in Zp to the power n. And well, that's why to solve this system, we had a method of trial and error for the systems over Zp. For the systems over R, however, we have now two methods. One is Gaussian, and the other one is called Gauss-Jordan elimination. Yes. Now we want to say that this guy also works here. We can do Gauss elimination or Gauss-Jordan elimination for systems over Zp. Well, we have to be just a little bit careful, because while reducing the augmented matrices, we sometimes subtract, or sometimes we multiply by 1 over something, inverse of something, basically divide. In ZPs, so this is a remark that you should keep in mind. There's no dividing. You don't have 1 over 2. What we have, everything, so all required elementary row operations for a system over Zp can be done by product or multiplication and addition. And we don't use subtraction. Well, in some ways we use, but not in the regular way, subtraction nor division. Okay, so let's see these things in practice, because the theory can go very deep and we can get lost very easily. Okay, so this is a system, two variables, two equations. It is over Zp. Something interesting here to note is that you see when there are 4 in the coefficients, 3, 2, 1, it means that, well, you have to work with some Zp, p bigger than or equal to 5. Well, in this case, we are working with Z5. Remember that to solve such a system, we can have, well, we have two components, so we will have 25 entries, 25 different vectors in Z5, 2. So you can plug in 25 different possible vectors and then check which ones are solutions. Here now what we do, we just try to do Gauss-Jordan elimination. Plug in, first find the augmented matrix. And now, well, we want to row reduce this one. This guy here is in the right place. It is 1. I will take as the leading one and use it to make everything else in that column, there's only 1, to make it 0. So it means what? It means that I have to multiply row 1 by something and add it to row 2 such that 3 plus box times 1 is 0. Yes? Well, how can I solve that? Well, box has only values 0, 1, 2, 3, or 4. And 3 plus box times 1 can be plug in 0. 0 times 1 is 0, plus 3 is 3. 1 plus 1 times 1 is 1, plus 3 is 4. 2 times 1 is 2, plus 3 is 5. 5 in Z5 is 0. So that means that this guy is going to be 2. In other words, we need to replace R2 by sum of R2 and 2 times of row 1. So 1, 2, 4, and here with 3 plus 2 times 1, and 1 plus 2 times 2, and 1 plus 2 times 4. Let's see, what does this give us? So this is 1, 2, 4. Remember, everything is done in ZP. Here's Z5. 3 plus 2 is 5. In Z5, that is 0. 2 times 2 is 4, plus 1 is 5. Again, that's 0. And 2 times 4 is 8, plus 1, 9. 9 in Z5 is 4. And here, first of all, this is row reduced echelon form. It is row echelon form. And the second thing you notice here is that, oh, we have 0 row equals to 4. In other words, if I write the equation for this row, it will be 0 equal to 4. Not acceptable. So the system is inconsistent. No solution. That's the other way of saying that. Remember, 25 possible vectors. You had to plug in all 25 and then compute all of those things to get to this decision that, well, the system has no solution. But now we just got it by one step of reduction, row reduction. Okay, let's do one more example. Okay, here I have a system in Z3 over Z3. Well, I'll start with the augmented matrix 2, 1, 2, 0, 1, 2, 0, 2, 2, 1, and 0, 1. First thing, choose one of these to make the other ones 0. Yes. Well, I can choose this one. Let's just choose this one. Replace row 1 and row 2. Well, interchange row 1. Sorry, interchange row 1, row 2, and this way we have 2 there, then 2, 1, 2, 0, and 2, 1, 0, 1. That's the first thing. So this is 1 in a good place. We want to use that to make this guy 0, this guy 0. Yes. So in other words, I'm looking for a box when you multiply to row 1 and then add it to row 2, we get this entry 0. In other words, 1 times box plus 2 needs to be 0. We want to kill this 2 there. Go find the values. So box here can be either 0 or 1 or 2. Then 2 plus box times 1 is 0 times 1 is 0 plus 2 is 2. 1 times 1 is 1 plus 2 is 3. 3 in Z3 is 0. Oh, that's it. That's what we need. So we will just add. Yeah. And also we want to make this other, well, do exactly same thing with R3 also, yes. This is nice. Now I have 1, 2, 0, and 2. Here we have to add 2 plus 1, 1 plus 2, 2 plus 0, 0 plus 2. Here 2 plus 1, 1 plus 2, 0 plus 0, and 1 plus 2. The matrix we get, this is not a row operation, just equality. We get is 1, 0, 0, 2. Remember, 1 plus 2 is 3. In Z3, we have to write it as 0. Okay, 0. And then this is 2. This is 0. And then we have 2 there. This is 2. And 2 plus 1 is 0. Wow, nice. Now, we are done with the first row. We move to the second row and go one by one. You see that, oh, okay, there is a 1 non-zero entry. We choose that one to make it 1. What is the number I have to multiply to row 1? Row 2. Such that when you multiply that entry 2 by that box, you get 1. I want to have 1 there. Okay, so there are 3 values for box, so either 0, 1, 2, and box times 2. 0 times 2 is 0, 1 times 2 is 2, 2 times 2 is 4. 4 in Z3 is 1. So we just found what is the box. Multiply row 2 by 2. So it will be 1, 2, 0, 2, 0, 0, 1, 1, and then 0, 0, 0, 0. Very nice. And you see that everything else in that column is 0. That means that we are in reduced row echelon form, and we can start doing the step 3, which is write down the equation for this guy. So this is x plus 2y equals to 2, and z equals to 1. How about y? Y is for a column without leading 1, so that will be the free variable t. In other words, I have x plus 2t equal. I want to take t to the other side. How can I do that? So here, x plus 2t is equal to 2. Well, you may say, okay, add both sides by negative 2t. I don't want to use subtraction or negative sign there, yes. Instead of that, I can say, okay, see, if I add both sides by t, this will be x plus 2t plus t equals to 2 plus t. X plus 2t plus t is 3t, but 3 times anything will give us multiple of 3, and that is 0 in Z3. So it will be x plus 0 equals 2 plus t, and that's x equal to 2 plus t. So in other words, we solve this guy. It is 2 plus t. It's very interesting. You see, completely different world. And then y itself is tz is 1. This means what? This means that we have equation. Well, the solutions for the system is this guy. Let me separate them. 2, then 0, 1, plus coefficients of t, 1, 1, and then there's no t in the last one. And well, something very important, t is coming from Z3. It means that t can be either 0 or 1 or 2. In other words, the solutions we get when t is 0, we get 2, 0, 1. When t is 1, we get 2 plus 1 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And when t is 2, that's another one. 2 plus 2 is 1. 2 times 1 is 2 plus 0 is 2. And 2 times 0 is 0 added to 1. So this system has exactly three solutions that we found here. Okay, so these are the examples that you see, and again, Gauss-Jordan elimination and Gaussian elimination can be applied for the systems over ZP. The key point is that we don't use subtraction and division. You just try each time to find right coefficient. You try to write a table like this and figure out what is the appropriate number to put for box.